So I think maybe an interesting point just to pick up from Marco, I think, is, and I've gone through other presentations here, has been the concept of a user. And I think it might not be completely clear to the audience what we mean by a user here. And I think Mitesh here is probably a good example of a user. He'll be angry at me now, but that's okay. In terms of that, it's a physicist within the collaboration that typically wants to find the Higgs or find some rare decay or whatever, and who do not really care about the computing. Okay, he nods, I'm still popular. So has a limited knowledge. Marco might have all the fine diagrams of this and say, users can only analyze data that comes out of the detector at XX hertz or whatever. They don't care, they just want the job done. So what I'll talk a little bit about is how they, as physicists that has a limited knowledge of the overall architecture, actually get their job done in the end. And so if you look a bit at the issues involved here, we've looked a lot of this already here, somehow starting out from up here, that an analysis is, to a very strong sense, a long data reduction problem. We start out with the trigger from the detector, we create some group data sets in one way or the other, that's a sort of organized way. We have a data selection further, we have some kind of fitting, figuring out what trends we see in that data, etc. And in the end, we write a paper on it to a journal, which to some extent also is a data reduction exercise. We try to express in a few tables and figures what we actually worked out about particle physics. So this one here, from a user perspective, is really the tricky one. It's the one that they don't really want to deal with, but somehow have to deal with at an individual level. You can no longer somehow delegate it to the computing guys to do anymore because they don't know what you want to do. You are the one that develops the algorithm for it, etc. Now you have to use it on the data. So all of the experiments at Large Hadron Collider rely on a distributed data analysis model in one way or the other. Marco already talked about this, how the data is distributed around the different of what we call these tier 2 and tier 1 centers around the world. And we use what we call grid tools to analyze this. These are relatively low-level tools. What Ganga does for the users, we'll come to a bit later, is to some extent to put an abstraction layer on top of that. One of the things we do take advantage of this is that we have what we call a grid certificate, which gives a single sign-on to the system. So you, as the physicist wanting to analyze the data, don't have to deal with somehow authentication in multiple layers. You get one authentication, and then you are permitted to whatever your collaboration have decided that you can look at in terms of the data and so on. So what is Ganga? Ganga is basically a programmable interface for the processing of data. So one of the concepts that it has been designed with is to ensure somehow that you can move from what a typical physicist would do naturally, which is to sit and develop code on the PC that stands in front of them, run on some data there, debug the problem, etc. So it has a concept that is somehow encapsulated in the configure once, run anywhere. So you can develop your code locally on your laptop or whatever. You can run on some test data there. You might use a local batch system where you have a very quick turnaround in the system. You get your answers back more or less immediately from it to test on a somewhat larger data set. Then you realize that you have to analyze these 20 million events that you don't really know where it's located in the world. You do that through interacting with one of these workload management systems here. You have the Dirac system here from LHCb here. To get it through. Of course, it doesn't work. Then you revert to the debugging stage down here on a local data set to figure out what's going on, etc. And the idea is that you can change between these different running modes simply by changing the configuration of this programmable interface. So this then brings, I don't think I'll say too much here, but that one of the critical points in a data analysis like this is indeed that you have to define somehow the division point between when you do something centralized for everybody at the same time, but not necessarily quite what they want, or that you allow every individual physicist that wants to extract some given feature of the data to do it individually. And at the moment, I think all particle physics experiments operate with an extremely static boundary between the two. There's no somehow kind of, what to say, clever caching of it or whatever. Now this is the 20th user that's requesting the identical information today. Maybe we should keep it. That's not something that's there in the system. But maybe what more important from the point of view of the processing is that the individual physicists, they just do this in what from the system appears like a completely chaotic manner. There are many people doing it, the LHCb experiment, not many by somehow, search engine standards, but there could be, a few hundred people involved in this here. Quite often they're inexperienced in what they're doing. Quite often they attempt to do large-scale data processing without having done that local testing stage first. So there's an enormous failure rate in this involved as well. So often it's very repetitive as well. And you somehow have to look at all this and integrate it in it. And in the LHCb experiment, we rely on a combination of these two here, the centralized production and the individual chaotic access to it. What Ganga deals with is mainly the individual aspect down here in LHCb. It's the only aspect it deals with of this. So how does a typical workflow for an analysis look like? Well, it's something along these lines here. You develop the code, you make sure that the architecture you're on is actually the architecture of a machine, you build the code, you copy some test data locally to test on, you debug it, you go around in this one here. Then you try to find the full data set in the bookkeeping of what you want to analyze, you divide it up, you send it to different sites, etc. You try to keep track of it, and finally you want to do the physics. The physicist only cares about this box and this box. All the rest is nonsense to them that they prefer never to deal with. So the idea in Ganga is to at least try to get to this stage here, that all the other steps are as much as possible automatized from the perspective of the physicist. So how does it work? In general, what Ganga does, it's an interface that's built entirely in Python. It operates basically with that you have a fully object-oriented approach where the job, the processing unit you want to have is basically specified through a set of boxes you put into it, what kind of application it is, that's where the physics comes into it, where you want to run it, do I want to run this locally, on the grid, on my local batch system, what kind of data I want to analyze, how do I want to, what rules do I need to apply in order to divide up my data in a way so I get it back in a decent time, etc. So all these codes here are provided as plugins into the system. If you come along and say that we want to process data, perhaps user analysis running on machines at Yandex, you could apply a backend somehow into the system that would allow a user to immediately start using that system. You have to put intelligence into that backend object, but the user wouldn't care. They would just select, I want to run at Yandex. It's programmable in the way that the user can interact with the computing jobs they're doing in a programmable way. Most of them do it writing very simplified Python code. They're not in general into fancy one-liners that will do it all there. But you can interact with the system. You can decide if something is failing in a programmatic way rather than somehow sitting on web pages and clicking up and down and selecting things ad infinitum. So just a final slide here, I think, on that usage outside LHCb, that the system we have developed, this Ganga system, is used in quite a few other places. It's very often actually used together with the Dirac system that Marco talked about as a way of getting physicists to analyze general types of data. We've seen it in many other projects within particle physics. I won't go into these names, they won't say anything. But also in other science areas, we've seen uses, mortar table modeling, flu virus searches, cryptography even. And also some commercial projects which have been funded initially basically coming out of Research Council funding schemes for this. Some interesting ones about image classification on the grid and also on modeling protein folding. So typical large-scale computational aspects where people want to get a programmable access to large computing resources. So what are the Ganga developments? I think that the future will certainly require that we follow up on developments and usage within core areas and, here I should say multi-core areas here. The access to multi-core machines, again, is something that Ganga somehow internally is not really dealing with in a particularly intelligent way at all. We have to follow up on the developments there. we have to deal better with the user support, inclusion of new paradigm scenarios coming down here. We also have to deal better with somehow, we have very much an abstraction in terms of the computing resources we are running on. I think it's extremely rare that an individual physicist knows where in the world their data was processed. They just don't care. But they still have to keep a too detailed knowledge about what data they're processing, how it should be divided up in chunks, what the data exactly is called. So that's an area where we would benefit from getting a larger level of abstraction onto it to basically make it easier for the physicist to deal with it. This here is just where it's documented, and also worthwhile saying that the whole Ganga code is released under the DPL to maximize the impact on it and make it usable in other areas without having too many strings attached to it. And that was it. Thank you very much.
Okay, thank you, Ulrik.